going on, reef builders and all my fellow Aquashella attendees? Thank you so much for coming out to my talk. It is so exciting to see so many faces out there, so enthusiastic about the topic of water flow in a reef aquarium. This is a presentation that I put together in college when I was like 25, 26. So I've given this talk many, many times. And one thing that you'll probably notice is that there's a lot more conversation and a lot more discussion about lighting, right? Lights are sexy, all the colors, all the brightness, it's something that we can really see and visualize. But water flow is a lot more challenging. So that's actually one of the reasons that I got into this topic in college. Dana Riddle and Sanjay Joshi, they were already really covering and smothering all the lighting topics. So I want to differentiate myself, and this is kind of how I guess, broke into the aquarium speaker circuit and started talking about water flow. So I decided to do actually a little bit of research that will be complementing this presentation. So back when I was in college, I had fancy title names like a presentation on hydrodynamics and the effects of flow and the biology of corals, trying to say it all. But we're just going to jump right into it. So as introduction, just to get your gray matter flowing and to get you thinking about some of the different ways that water flow is more important than light. Which is more important? Is it water flow or is it light? I think you know where I'm going with this, so we'll just keep moving. How many coral species can live without light? If you think about it, there are hundreds of species of corals, maybe thousands, that are non-photosynthetic, that live at the bottom of the ocean, that live under other corals, that live in caves. So there's hundreds of corals that do not live without any light or don't require light to live. But if you flip that question, how many corals species can live without water flow? And there really aren't many marine environments where there is no flow. The only place I can think of are like intertidal habitats when the waves go down. But short answer is there's none. There are no species that can live without water flow. I like those fancy animations that I made when I was really invested in my PowerPoint presentations. All right, so we're going to keep going. Even in the case of a photosynthetic coral, so a coral that all of us keep, something that we're very familiar with, how long can it live without light? We know that, all our tanks get dark at night, and so they can live days, maybe weeks, especially when they're being shipped, when they're being collected, not really kept in the kind of nutritious lighting that they require. So photosynthetic corals can live a long time without light, days, maybe weeks. Some of us have kept frags and colonies and stuff in our sumps for periods of time. But if you take that same coral, how long can it live without flow? You know that some of the biggest coral issues, tank problems happen when you don't have water flow. And if your power goes out, your corals might live hours, maybe a few days without water flow. So water flow is important for many different factors of coral biology. It's important for food capture. Corals don't really walk around, so they need water to bring them food. To rid the coral of waste. And to disperse their spawn and that gamete. So corals, they're sessile animals. They don't move. But the most important reason that we need water flow for our corals is respiration and photosynthesis. And that's basically, breathing and creating energy from light. So this is going to be kind of the main context in which I'm going to be discussing water flow relative to corals. So some previous studies have shown that corals maintained in stirred water flow chambers show higher rates of photosynthesis than corals in still water. And during bleaching events, this is a really big one. You guys know about bleaching. Everybody know about bleaching? Yeah, whoa, yeah. So when there's bleaching, a lot of times there'll be a big old field of corals that are really white and not doing really well, but there'll be certain locations, little spots where the corals are actually doing well, and that's usually attributable to little areas of water flow, like localized water flow that's keeping the corals kind of flush during that high temperature event. Also, some scientists have transplanted corals from areas of high to low water flow, and they showed decreased growth rates. Yeah, we all know how important water flow is to aquaculture, and the same thing out in the wild. And another one is, we've all grown corals under different flow regimes, and you know that under high flow, they're going to grow thicker and a lot more branchy, and in low flow, they're going to be thin and a little bit spindly. So this is an example of what's called morphotypic plasticity. I know that's a mouthful, but these are actually some corals that I grew 15 years ago, but these are the exact same strain. And so I'm getting ahead of myself. So they were kept in different tanks. The coral on the left was kept in low flow, as you might expect, really open branch form. You got a good view over there? Yeah, big screen. And then the coral on the right was grown under high flow. The thing about this is the coral on the right took about twice as long to get to the same occupied volume, but it has a lot more polyps for that particular colony. So the coral on the right technically has a lot more polyps to breed. So this is a much better colony of that coral for a given space. So what do we already know about coral physiology? Is there's a very positive relationship between coral health and water flow. And when corals experience heat stress, like when our AC goes out or there's a bleaching event, water movement can be critical to their survival. Also, corals can acclimate their body to the water flow. So let me just show you the heart of my research. This was the flow chamber, and this is basically a recirculating device. On the left, you have some stuff called Hexcel, basically a bunch of straws squished together to straighten out the water flow. So this is a recirculating chamber. It's only sealed, and I would put these little nubbins of Posloporid ammocornis in the visible side. And this was an attempt to measure basically oxygen consumption and oxygen production under different flow regimes. So before I show you the raw data, this is an example of a photosynthetic curve. This is what the oxygen does on the y-axis. On the y-axis, you have maximum photosynthesis in terms of oxygen, and on the x-axis, that's light intensity in terms of micromoles. So you see here at the bottom, there's no light, so the coral's actually consuming oxygen. And you get to this is called the respiration. And then you get to a point where, compensation point, where photosynthesis is equal to respiration. So this would be a net zero change in the oxygen concentration of the water itself. And that's really important because that means 50 micromoles, which we are somewhat familiar now in terms of PAR, that is the level at which the coral is not spending energy to breathe, to be alive. So anything more than that, and that's just within this coral, right? This does not apply to all corals. These corals are acclimated for this. And then you have your first kind of milestone in terms of lighting intensity. So these corals were adapted to high light, and you'll see I got about 450 micromoles, and this is called maximum photosynthesis. So you give the coral even more light, and it's just not going to produce so much. It's just like driving an engine as fast as you can. 6,000 to 8,000 RPMs, you're still going the same speed. And then when you give the coral even more light, you get what's called photoinhibition. And so on a short time scale, this is actually not a big deal. Corals are actually used to this. They will actually shut down and you give them more light, and they know that they don't want to be exposed to more light. On the y-axis, we have the oxygen consumption. So this is the test results just under darkness, but at different flow speeds. And the flow speed's measured in centimeters per second, so just like a straight line, right? And you'll see this is about as positive of a correlation as you can possibly have in the data. This is the most beautiful thing with the R-squared of 98. So that means that 98% of the data that we're seeing, all 3 points, are all being controlled by the flow that the coral is exposed to. And so here you'll see those same 3 points on the y-axis. So those are the same 3 points. Now I took those corals and I put them under different flow regimes, and you'll see that the lowest flow speed, this is where they all kind of intersect, right? So even at the same flow speed, for some reason, the compensation point was the same, right? Because under higher flow, the coral's consuming more oxygen. Same thing with low flow, is consuming less oxygen. So they kind of converge at about the same point. But you'll see the yellow line is a kind of a low flow regime, so the coral's under low flow. The pink line is a medium flow, and the blue line is a high flow. And you'll see that the more flow you give the corals, the more oxygen it actually produces. So that's the photosynthesis that we're talking about in our corals. And you'll see the same kind of maximum photosynthesis point is pushed further and further. So what you should be taking from this graph is that there's no such thing as too much light. There's no such thing as too little light. There's no such thing as too high temperature. All of this stuff works in conjunction, right? So there's only too much light for too little flow, right? Or too little light for too much flow. So what I really want you to see from this graph is that the more light you give a given coral, the more water flow it's going to need. That's really, really important. If you have still water, or a tank that doesn't have a lot of water flow, you really should be giving them lower light. But if you give them a lot of light, they're going to need a lot of flow to get rid of that oxygen. Yes, sir. It's so he asked about maximum water flow, and that's kind of a tough one because, as you saw in that previous image with the thin branch Poecilophora and the thick branch Poecilophora, the thin branch is adapted to it, right? So you could take that thin branch one and give it the flow that the thick branch one was under, and it's not going to be happy, right? Because it's trying to slow the flow down to the right speed between its branches, right? But if you ramped it up over a few weeks or months, it would develop that thick flow, those thick branches to handle that higher water flow. Does that make sense? And we know from shrooms and euphyllias that they don't like to be blasted. But one thing I do like to do on my reef tanks is, to keep the euphyllias as open as possible. They get a pretty gentle water flow throughout the day, going back and forth. And then 3 or 4 times a day, I put the washing machine cycle on, right? Because, they have big open skeletons and a lot of detritus can settle inside the skeleton. So instead of getting there and basting it all the time, I just turn the pumps way up and just really storm it out. So the euphyllias will definitely adapt to it, but they're not going to be big and puffy and luscious like we want them to be, except for torches, right? Those torches, they like that washing machine cycle. All right, so like I said, respiration shows an increase with an increase in water flow. The more flow you give the corals, the more it can breathe. And corals show an increase in photosynthesis that is closely associated with an increase in water flow. So that's basically summarizing what we just talked about. So why is this happening? So during peak photosynthesis, when the coral is getting as much light as they can possibly handle, it's actually oxygen that builds up inside of their tissues, right? We all think of oxygen as a really good thing, right? We like to breathe, or corals like to breathe. But the thing is, corals did not naturally evolve to photosynthesize, right? The corals are not doing the photosynthesis. It's the algae inside their tissues. So the corals kind of have to deal with it, right? And so when they get a lot of oxygen inside of their tissues, if you don't have enough water flow, that oxygen turns into free radicals, right? Anybody here heard of oxygen-free radicals? Yeah, so that's actually detrimental to your cells. So the coral's desperately trying to get that oxygen out. That is actually, you don't know this, but the entire name of the game of reef keeping is getting oxygen out of your corals, right? You think we need to give them light, we need to give them flow, but actually everything that we're doing, we're trying to get the oxygen out of the corals. I know it sounds kind of weird. When you give the coral more water flow, that decreases the oxygen inside the tissues of the coral, and then it's able to photosynthesize more. So this is actually comparable to a lot of everyday examples, right? If you have an engine, you gotta have a certain amount of air with the oxygen inside to combust, but you also need to get rid of that waste heat. So you need a big old radiator. So that's how, that's what corals are doing. So same thing with your computers, right? You apply more voltage to your CPU chip, you gotta get rid of that waste heat in order for your CPU not to thermal throttle. I think it's kind of funny, we can talk a little bit more about thermal throttling. That was really a geeky topic 15 years ago, but I think a lot of people know about that with our phones and our laptops and stuff like that. So this is the same thing with corals. The more water flow you give the corals, the more it can get rid of oxygen. Same thing in your computer. The more you cool your CPU, the more voltage you can put into it and drive it a little bit faster. A lot of people ask me, well, just like this gentleman, well, what's the ideal water flow? And it really depends on your corals and what they're adapted to. This talk was really crafted around a totally different era of reef keeping. For those of you that join us a little bit later, I said that this talk, I first gave it in 2005, 2006. I've given it in French, I've given it in Italian. This is the 4th or 5th version of this particular PowerPoint. in that age, we were using metal halides, and everything had to be super duper 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 bright. I think I need to revisit this and talk about minimums instead of maximums, because we're not, growing aquaporas and recreating that shallow water reef is not as much of our focus today as it used to be. Today we just want happy, healthy, colorful, well-expanded corals. But a good baseline is for up to about 100 micromoles. And I used to use T5 and VHOs and metal halides as an example for this. But let's just say a lower light coral tank. Not full-on shroom and zoanthids, but a little bit more chalice, euphyllia. So from 0 to 100 micromoles, and that's going to be, just kind of some basic strip lights, probably without individual lenses. You probably want to flow speed of 7.5 centimeters per second. And as you ramp up that intensity from 100 to 400 micromoles, 400 micromoles of PAR is probably, just like the good sweet spot of a Kessel mounted 2 feet above the tank, or Hydra, or Radion, or a lot of lights put together. But as you ramp up that lighting intensity, you definitely want to increase the flow speed up to about 15 centimeters per second. I know the question's coming. I'm going to answer it before you can ask it. And then, beyond that, you actually need to ramp up your water flow speed. So this is something for you to consider. When I put together this talk, our lights were not controllable. Our pumps were not controllable. This talk was created before propeller water pumps. Who remembers a time before propeller water pumps? Before wave makers, Maxi Jets, Otto, Hagen 802. You know what I'm talking about. This guy knows what I'm talking about. Top mounted pumps. But now we have controllable lights and we have controllable pumps. And I think most of us probably set it and forget it, right? We just kind of set a couple programs and you don't think about it ever again until you reprogram the pump, or you put it on a new control platform, or you get some new corals. But this is the graph I want you to try to burn into your mind. Your lighting schedule now is dynamic. There's so few lights and pumps that aren't controllable now. What we should be trying to do with your light is just have a gradual increase all day long, just like the ocean, right? Not a 1 hour ramp time, not a 2 hour ramp time, but like a 4 to 6 hour ramp time. That is the most natural thing. And then, if you have controllable water pumps, make them do the same thing, right? I talked about my washing cycle that I like to do a few times throughout the day, just kind of give it a little surge, a little storm mode, kind of flush things out. But from this graph and from this data, what you want to do is ramp up the intensity of your pumps to kind of match the intensity of your lights. Does that make sense? Just like the cell phone example, just like the home-built computer example. More voltage you put in there, the more heat you're going to have to get out. And so the next question is, what do these numbers mean? 7.5, 15, 20. These are centimeters per second, right? This is the speed of the water. This is why I really like to encourage people to create gyre flow. Ever heard of gyre pump? The name gyre came from this presentation like 15, 16 years ago, right? I remember introducing gyre flow, and no one knew what I was talking about unless they were an oceanographer talking about ocean gyres and ocean movements. But basically, you're trying to make all the water go in the same direction. All the water go in the same direction. And I'm going to get into the random, chaotic, turbulent flow and why that's a little bit confusing. But people always ask me, well, how do you measure water flow? Well, if you get your water moving the same direction, it's never been easier. You can literally take your cell phone, if your water's moving kind of one direction, put real fine flake food in there, and just film it in slow motion. And maybe you have a ruler taped to your tank, or you take that video, put it on your monitor, put some wax paper over the monitor, and just kind of watch the particles and just count them. See how long it takes for them to travel so many centimeters or inches per second. But the thing is, it doesn't have to be that exact, right? If you're trying, if you're thinking, in a larger tank, it's a lot easier, right? You got a 3 or 4 foot tank, and you have mostly unidirectional flow. How long does it take for the food to get from this side to that side, right? And then you just do some very simple math, and then I'm in the 10 to 15 centimeter per second range, so that's 4 to 6 inches per second. If you're the kind of person to do that, your flow's probably already good, right? If you're paying that much attention to your environmental parameters, you're probably already good. Again, this data that I'm talking about is a lot more applicable to, the maximum, the highest range. But I feel like, we've all been talking about PAR for a long time and trying to, measure PAR. But really what goes along with that is the speed of the water flow. You got to match those things up, especially if you're talking about highlight animals, except for clams, because they can breathe on their own. All right, so that's kind of the data supporting why it's important, why water flow is more important than water itself. That's a little joke, but water flow is definitely more important than light. All right, so some terms that I'm going to discuss here. Basically, the next 10, 15 minutes, I'm just going to talk about how to make better water flow, right? And some of the terms, gas exchange, mass transfer, mass flux, diffusion, kind of all means the same things. And we're just talking about particles kind of, going into or out of the coral or of just water. So the rate of gas exchange, including what we're doing right now, breathing, this is dependent on the availability of moisture, right? You cannot dissolve something across no aqueous boundary. I'm sure there's some exceptions that someone will correct me on one day, but you need moisture, you need a high surface area, but the most important thing you can do is create a high gradient, a big difference between the inside and the outside. And that could be anything. That can be us breathing, that could be temperature, that could be warming up, that could be baking a cake. So we're all sitting here right now breathing actively, right? We have specialized organs for breathing. We take it for granted. But not only do we have the lungs, they have a very high surface area, all the way from the beginning all the way to the end. And this is an active process, right? So we are giving our lungs airflow in order to keep that gradient high. And if you look at a lot of other animals, they also have very specialized breathing apparatus. So fish have their gills, crustaceans have internal gills, and insects have trachea. You guys all know about nudibranch. They have, these little branchy things sticking off on the back. And if you look even closer, like at a feather duster, there's a huge surface area. If you ever see this under a microscope, you can actually see the single capillary, the single file of blood cells going up and down every single one of those little pinnules. So they have a very specialized, almost everything has a specialized way of getting rid of CO2 and bringing in oxygen. This is also how they get the chemicals out of the water, or the elements out of the water. But if you look at corals, they do not have this. They do not have a specialized breathing apparatus. The whole coral is the gill. The entire coral is the lung, right? They have a little bit of tissue on their skeleton. Got some polyps sticking out in the water. And in the case of soft corals, they have some little pinnules on their tentacles. But every little bit of that surface area is specifically for the gas exchange to interact with their environment. But it's very passive. So if you were, this is one of my famous lines, if you were trying to breathe like a coral, you'd have to rip your lungs out of your body, turn them inside out, hang out on a hill, and hope that the wind blows strong enough, right? Think about this when you're looking at your corals. Imagine yourself standing on your hill with your lungs in your hands, just hoping that the wind blows enough for you to get a good breath. All right, so another concept, throwing a couple at you, but another one to think about is, have you ever wondered why copepods don't have fins, right? They have little bristles and they have arms, but they move around the water. At the scale of a copepod, they can actually grab the water. It's like moving through syrup that they actually also happen to be breathing. And that's because at that scale, water is very viscous. And what you need to think about for your reef tank is there's a microscopic layer of water that is glued to your corals. It's glued to your rocks. There's an infinitesimally small, thin section that never moves off the rock, right? Just like surface tension, right? You can put your hand in water and you pull it out, you still have water in your hand until it drips off and evaporates, but until it evaporates, you still have that microscopic layer on your hand. And this is the same thing in our reef tanks. And as you move further away from that surface, the water's sticking to itself, but there's an area where the water flow that's moving past is drastically slowed down. This is called the momentum boundary layer. Don't have to remember that name. You just have to understand the principle that there's a thin layer of water next to your rock. No matter how much the water's flowing here, there's a thin layer right here that is just not really moving. And you'll be able to apply this because, we've all seen those frags. You glue a little small frag, a little tiny frag, little bitty, bitty, bitty frag, and it just sits there and looks at you forever and ever and ever, and encrusts and encrusts. Once it got a good base, it's like, all right, in nature, it needs to encrust so it doesn't blow away, right? But as it starts growing a little faster and a little faster, and then the boundary layer is a gradient, right? There's not like a demarcation where all of a sudden you're out of the boundary layer. Once that frag gets about, 1 inch tall, in most flow regimes, it's getting out of that boundary layer, and all of a sudden it can actually experience the flow like a full-grown coral. And you guys have seen this, right? You grow a frag, and it just grows slowly forever, and then it hits a certain length, and it explodes into, hopefully you've seen this. We're talking mostly about SPS and acros and branchy corals. So think about this in your tank. If you have an area of lower water flow, there's going to be a bigger boundary layer where those corals are not getting the kind of flow that you're seeing all throughout your aquarium. You really need to think a little bit dynamically. I would say less about changing your water flow and more about where you put your corals, right? We want our acros, all our SPS, Montes, we keep them at the top. That's going to put them in much better flow. This is a little bit more common knowledge now, but if you're working with frags, just don't assume that the mainstream flow is going to be the same as the bottom where they are at. All right, so this is the origination of gyre flow. One of the things that you can do, and some people do this accidentally, is getting their pumps to work together. Who here has ever heard that your flow needs to be random, chaotic, turbulence? If this is a coral that I'm holding very intimately close to my mouth, it does not care that the water flows random and chaotic and turbulent over here. Like, it's true. You want some of that random chaotic to break down the boundary layer, but Coral Man does not care about, random flow over here. The random flow needs to be right next to the coral. If you're driving a car down the road at 15 miles per hour and you hit a tree, you're not going to scramble your brain. But if you drive down the road like a madman at 100 miles per hour and you wrap yourself around a pole, you're going to have a lot of turbulence in your brain. What I'm trying to get at is the randomness and the turbulence needs to happen where the coral is. It does not matter what's happening in the open part of your tank. That is beyond useless to the biology of your corals. The turbulence needs to happen at the coral to break down that boundary layer. And like I said, you can increase your water flow, but I think these days our water flow is actually getting pretty good. We have such great access to flow. Think more about where you place your corals within your aquarium. And so one of the things that I did to start experimenting with this is I created gyre tanks. So this is a 33 long with a divider basically flush from front to back with just a little opening at the sides. And I'm not sure if they make these anymore, but there's a Rio Sayo on the left. That was top of the line when I took that picture. That was one of the most affordable little propeller pumps you could get. But this small, cheap, 5-watt little propeller pump moves that entire tank. Because if you move a little cross-section of that water, what happens to the water behind it? It has to come in and fill it in, right? What happens when it gets to the end? Well, it's got to go around the plate. What happens when it gets to the other side? It's got to drop. And so you build up this momentum. So this is an extreme case, right? But you build up that momentum, and this is an awesome, awesome design for a frag tank. People are kind of unconsciously doing that these days. With egg crate, you push a lot of water flow underneath it, and you know that some of the water is going to come up, but it'll kind of stick together and come around. So this is an example of a horizontal frag tank, or frag gyre tank, and this is a vertical frag tank. Oh man, I forget who did that. He's out of Arizona. Aqua, yeah, that's not helping. But this one is basically the same idea. There's a vertical panel, flush with the bottom, flush with the top, all the pump and equipment's in the back, and that helps to spin water around this plate for the gorgonians. And then this is the 180-gallon coral tank that I took care of in university. It's got a weird centrally mounted overflow. but I was able to flow this entire 6 by 2 foot tank with maxi jets. You can see it up there in the top left corner. And basically 2 maxi jets would be in opposite corners, basically pointed across the tank to help spin the water. And then the other 2 maxi jets would turn on while the other was turned off and spin it back around. But these are like extreme examples. But one thing you should try to do in your reef tank is, people always think I'm going to tell them to get bigger, stronger, more pumps. No. What I like to tell people is try to move a cross section of the water in your tank. When you have mass water movement, if you move a certain amount of that water, all the rest will follow. You know, so I hope that's been some insight into water flow and how it works for our corals. I want to thank everybody for coming. I know there's a lot of juicy, pretty stuff to look at. You know, really means a lot to me that you guys beelined here to see this talk. Thank you so much to Aquashella for having me out, putting on such a fun event. I'm excited to go look at the booths, and I'll take any questions you have now.
In the beginning, you said that oxygen can prohibit the growth of corals, and that's not necessarily a good thing. But I'm sure I'm not the first here to forget to refill my RODI unit, or the water, the fresh water. And when I see those super, super small white air bubbles, how do those affect corals individually, the individual air, if they do at all?
So the oxygen that we're talking about, you can't see it, right? It's just diffused in the water. So he's asking about air bubbles, you know, getting into your tank and how that might negatively affect your corals. This is like totally unrelated, but I don't know, you know, even with the best water flow, even if you try your hardest to have flow all throughout your tank, you can't hit it all, man. Especially as stuff grows in, especially if you have a ton of rock, especially if you have like a rock with a ton of matrix. So what I used to do is actually create a storm, you know, go with my baster and base stuff around a lot, or take a little power head and kind of blow it around. But now we have such strong pumps, I actually turn the entire tank into a skimmer. I'm not kidding. About, depending on the tank, you know, some of the ones that are medium flow and tend to build up a little bit more waste, I literally take a very strong air pump and a wooden air stone, and I stick it right in the water pump, and I turn the entire tank into a skimmer, and it really helps to lift out all that junk. But that's you know, that's something I install for like 1 day, twice a year, maybe. Maybe I'll go a year without doing it. Maybe I'll do it every couple months, whatever I'm feeling like. But that's actually a cool way to kind of do an intense cleaning. You know, our tanks are, most of y'all are probably not getting elbow deep in your tank all the time. I am. I'm always in there, always poking at stuff. But if you leave things alone for a year or 2 years, that detritus can build up. So that's a fun little technique to kind of lift away the waste. And you'll see your corals actually surprisingly like it. They'll slime, but it's not like an irritated slime. It's a really clear mucus. And you know, most of that funk, because the water flows still on, will rise to the top and go down to the filter. So that's kind of a fun aside. I don't know how related that was to your question, but I would actually use that technique rather than worry about it. Any other questions about water flow or corals or anything while I got you? So he asked if anybody has Acropora Florida. Acropora Florida is not from Florida. Oh, I know who you can talk to. We'll talk to Chris at ACI, because he's been farming them. He's a wholesaler, but he would be the guy to tell you. And so, yeah, I gave him a bunch of chunks, and he grew it out. So if you don't know, Acropora Florida is like an awesome coral. It looks so bright, it makes green slimer look dim. And no joke, it looks like you took a coral skeleton and broke a highlighter pen and just let all the ink drip onto it. It is so freaking bright. And it's like a 20-year-old coral strain by now. So yeah, the Toxic Florida, that's a really, really fun one. Yeah, go ask Chris at ACI. He'll talk your ear off about it for a while. Yes, sir, you're gonna have to speak up. How do you determine if you have enough water flow? Well, so you might have missed the first part of the talk where we talked about maximum photosynthesis. We're not bumping against that limit anymore, right? We're not using really strong metal halides and tons of VHO and lots of T5. The reef aquarium hobby lighting these days, most folks are really kind of middle of the road. So it's not about having too much flow or enough flow, it's enough flow for the lighting. You need different kinds of water flow for different periods of time. You know, instantaneously, the coral needs some water flow to help drive the removal of oxygen. Throughout the day, it needs, you know, the waste to be driven away. My general prescription for all of you, and I think this would be a good point to leave off, is do the flow that you think makes sense. You know, just use your pump however you feel is comfortable. Try to position your power heads or wave makers closer to the water surface, because that is going to move more water than if you put it at the bottom, right? There's less friction at the top because of the air. The water can move more freely than at the bottom, where it has to run into more water, right? So step one, move your power heads and outlets and wave makers closer to the top. I mean, just to the point where it's starting to suck in air. But then, because we have a lot of programmable pumps these days, introduce a 10 to 30 minute cycle, 2 to 4 times a day, where it's blasting, where it's ripping, because that's going to help flush all the waste and detritus periodically throughout the day. If you have euphyllias or shrooms or something that you want to open up during the day a little bit more, make those wash cycles at night. But like I said, this talk was really when we had such substandard power heads. And it's kind of fun to rediscover some of these concepts with you as I'm giving it to you, you know, with new equipment, new pumps, new lights, new controllability. So yeah, short answer is, you know, just do a reasonable amount of flow. And because we have so many controllable pumps, just put a 10, 15 minute cycle on there where it's just going kind of like crazy and blasting things and almost knocking them over. And that's going to help you flush out a lot of the waste. So thank you guys so much for beelining here. And I hope you guys really enjoy the show and the rest of our speakers. And don't hesitate to talk to me anywhere you see me. Thanks a lot, you guys.